Module 6, Lecture A, K-means clustering. By the end of this lecture, you will be able to explain how unsupervised learning differs from supervised prediction in engineering analysis, implement K-means clustering with manual centroid assignment and update steps, and interpret clusters cautiously using plots and engineering knowledge. Unsupervised pattern discovery. No labels. In unsupervised learning, the data has no predefined labels or known answers. Instead of learning a direct link from inputs to outcomes, the goal is to discover patterns within raw observations, such as temperature or pressure readings. In engineering, this can help identify similar operating states, distinguish machine behaviors, or reveal recurring patterns that have not been named. In unsupervised learning, the absence of labels makes it difficult to judge correctness because there is no known target to compare against. For example, clusters in manufacturing data do not automatically reveal which parts are good or defective. At the same time, this lack of predefined outcomes lets engineers explore unlabeled data, such as energy use or vehicle telemetry, to discover useful patterns and insights. With unlabeled data, clusters are not fixed truths. They depend on the features, methods, and assumptions used to define similarity. Different aircraft engine measurements, such as fuel flow, exhaust temperature, or vibration, can reveal different kinds of patterns. Because there are no labels, engineers must interpret clusters using domain knowledge and context to give them meaningful explanations. Python code, no labels. Explore unlabeled engineering data by looking for patterns rather than making direct predictions. Compare prediction-focused methods with pattern discovery, and use engineering judgment to interpret what the resulting clusters mean. This note means the code should run without installing anything extra. The needed libraries are already included with standard Python or are commonly available, so you can focus on how the code works instead of environment setup. We import NumPy for efficient numerical work with arrays and mathematical operations, and use Matplotlib's plotting tools to create graphs and visualize data patterns. To generate repeatable synthetic operating measurements, a random number generator is initialized with a fixed seed of 7. It then creates 18 samples with 2 features, drawn from normal distributions with means of 22 and 3, and standard deviations of 1 and 0.4. This produces consistent test data that follows a normal distribution pattern. A second synthetic dataset is created to represent a different operating condition. Using a normal random distribution, it generates 18 unlabeled two-dimensional points with feature averages of 31 and 6.2, modeling a high-load pattern. The normal and high-load observations are combined into one dataset by stacking the 2 arrays vertically. The combined data contains all observations without labels showing where they came from. A shape check confirms that the result has 36 observations and 2 features. We start the clustering process by manually choosing 2 initial centroids, one at 21 degrees Celsius and 2.8 millimeters per second, and another at 32 degrees Celsius and 6 millimeters per second. These 2 points match the two-dimensional structure of the data. In methods like K-means, the chosen starting centroids can affect the final clusters. To assign data points to clusters, compute the Euclidean distance from each point to every centroid, using reshaped arrays so the distances can be calculated together. This produces a distance matrix with 1 row per point and 1 column per centroid. Each point is then assigned to the centroid with the smallest distance, giving an array of cluster labels. Centroids are updated by taking the average of the observations assigned to each cluster. For each cluster, the assigned data points are selected and averaged across their features to form the new centroid values. Finally, the updated centroids are checked to make sure all values are finite and no invalid numbers were produced. The messages explain that supervised prediction needs known target labels, while the current data has features but no answer key. Because there are no labels, k-means clustering groups observations by similarity rather than by a known truth. Engineers must then use domain knowledge to decide what those clusters mean in context. This plot visualizes clustering results by showing each observation as a colored point based on its assigned group. The updated centroids are highlighted with large red X markers, making the cluster centers easy to identify. The axes label temperature in degrees Celsius and vibration in millimeters per second, with a grid added for readability. This script shows unsupervised learning with a simple pay-means clustering example. It creates unlabeled temperature and vibration data for normal and high-load conditions, then groups the points by their similarity to two centroids. After assigning points to the nearest centroid, it updates each centroid using the average of its assigned points and displays the resulting clusters. The key idea is that clustering finds patterns without true labels, so engineers must interpret the groups using context. Prediction versus discovery. Supervised prediction uses labeled historical data to train a model and test its accuracy on known outcomes. Unsupervised pattern discovery has no predefined answers. It groups data by similarity, such as with k-means clustering. This is especially useful in engineering, where sensor readings and operating logs often lack clear categories but still contain meaningful patterns. Prediction and discovery are evaluated differently. In supervised prediction, you compare the model's output with the expected answer and measure errors. In clustering, there is no single correct grouping, so the goal is to judge whether the discovered patterns are coherent and useful. For example, pump data clusters may highlight operating conditions worth investigating, but they show similarities in the data, not the underlying causes. Unsupervised discovery, such as clustering, is more interpretive than supervised prediction because there are no labeled answers to check against. Instead of relying only on performance metrics, results must be judged with visual patterns, domain knowledge, and context. Clustering is useful early in analysis because it can reveal unknown groups, unusual cases, and patterns that guide further engineering studies or experiments. Python code, prediction versus discovery. Compare prediction with discovery by focusing on the main goal of the analysis. Use small engineering measurements carefully, and treat clusters as tentative patterns rather than definitive conclusions. The script begins by importing NumPy for efficient numerical work with arrays and mathematical operations. It also imports Matplotlib's plotting tools to create visualizations. Together, these libraries prepare the environment for computation and data visualization. The dataset is created with repeatable random behavior by setting a fixed seed in NumPy. It then defines paired measurements of pump flow rate in gallons per minute and vibration level in inches per second. Together, these values represent the relationship between flow and vibration in the pump system. Flow and vibration measurements are combined into one two-dimensional matrix using NumPy's column stack function. Each row contains one matched pair of measurements, and an assert check confirms the matrix has 8 rows and 2 columns before further analysis. We initialize the clustering process by manually choosing 2 centroids from the dataset, the first and 7th data points in the combined feature set. These points are stored as floating point values to support accurate calculations. The resulting centroid array is checked to confirm it has two centroids, each with two features. In k-means clustering, the centroids are refined over 4 iterations. Each time, the algorithm measures the Euclidean distance from every data point to each centroid, assigns each point to its nearest centroid, and then updates each centroid to the average position of the points in its cluster. Repeating this process gradually improves the cluster centers. The code contrasts supervised prediction, which needs labeled target answers, with unsupervised discovery, which looks for patterns without labels. It uses k-means to group similar pump measurements and then reports the cluster centers rounded to 2 decimal places. The key caution is that clusters can guide further questions, but they are not definitive engineering conclusions. This plot visualizes flow rate and vibration data as a scatter plot, with port colors showing the cluster each data point belongs to. The cluster centroids are emphasized with large red X markers, so they are easy to identify. Axis labels provide the measurement context, and the title highlights that the clusters were discovered without known target labels. A lightly transparent grid is added to make the visualization easier to read. This example contrasts prediction with discovery using k-means clustering on synthetic pump data. It groups flow rate and vibration measurements into clusters without using predefined labels, then reports the final centroids as the average characteristics of those groups. The key point is that unsupervised learning does not give definitive answers. It reveals patterns that can guide further engineering investigation. Engineering interpretation. Engineering interpretation turns patterns found by unsupervised learning into useful insights. Because these methods reveal groups or trends without explaining what they mean, engineers must connect the patterns to real operating conditions and domain knowledge. This step ensures the results are meaningful and relevant to the system being studied. Unsupervised methods can reveal patterns, but those patterns are not always meaningful or useful. For example, vehicle clusters based on fuel use may reflect engine condition, driver behavior, load, or operating conditions rather than true inefficiency. Engineers should interpret these results carefully and check that the patterns are stable, explainable, and consistent with the real system before making decisions. Clusters in engineering data should not be treated as real categories without supporting evidence. Visual checks, summary statistics, and domain context help determine whether patterns are meaningful for design or operations. For example, water network clusters should be compared with factors like pipe age or pump schedules, and biomedical clusters need expert validation before being linked to diagnoses. Unsupervised learning is best seen as a discovery tool that points to patterns requiring real-world interpretation. Python code, engineering interpretation. When interpreting clusters, connect the patterns to the engineering context rather than treating them as automatic explanations. Because unsupervised groups do not come with labels, their meaning should be described cautiously. In this example, the clusters are interpreted through the lens of fleet operations. The script begins by importing NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. These libraries provide the foundation for the data processing and plotting tasks that follow. We set the random number generator to a fixed seed of 7, so it produces the same random values every time the code runs. This makes results reproducible and easier to debug, especially when creating consistent datasets for testing and analysis. We generate synthetic fleet data for 2 operating conditions: light loads and heavy loads. Each group contains 10 samples, with payload and fuel economy as features. The light load data is centered around 8 tons and 18 miles per gallon, while the heavy load data is centered around 15 tons and 11 miles per gallon. These two datasets will be combined for later clustering analysis. The light load and heavy load observations are combined into one dataset using NumPy's vertical stack function. This creates a single array with 20 rows and 2 columns, so all data points can be processed together. An assertion then checks that the dataset has the expected shape before the next steps. We start k-means by manually choosing 2 initial centroids, one at 7.5 and 17, and another at 14.5 and 12. These points give the algorithm starting locations for forming clusters. We also check that the centroid array has 2 rows and 2 columns, confirming there are 2 two-dimensional centroids that match the dataset. The k-means update runs for 4 iterations. In each iteration, it measures the Euclidean distance from every data point to each centroid, assigns each point to its nearest centroid, and then recalculates each centroid as the average of the points in its cluster. Repeating this process gradually moves the centroids toward the centers of their assigned clusters. The process summarizes 2 labeled clusters by selecting the data points in each one and calculating their average load and fuel economy. For each cluster, it reports the number of vehicles, the average load in tons, and the average miles per gallon. This gives a concise description of each cluster's characteristics, without making claims about why the patterns occur. The message warns that clusters can reveal patterns in data, but they do not prove what caused those patterns. Engineers should interpret clustering results carefully and compare them with operational factors such as routes, payloads, weather, and maintenance records. This plot visualizes vehicle clustering by showing each vehicle as a point based on average payload and fuel economy. Point colors indicate cluster labels, while red X markers show the cluster centroids. The axes, title, and subtle grid provide context and make the k-means patterns easier to interpret from an engineering perspective. This script uses simulated fleet data to demonstrate basic k-means clustering. It creates 2 groups of vehicles with different load and fuel economy patterns, then repeatedly updates manually chosen centroids to form final clusters. The results summarize each group by average load, miles per gallon, and vehicle count, with a scatter plot showing the cluster separation. The key takeaway is that clustering can reveal useful operational patterns, but it does not prove causation and should be followed by further investigation into factors such as routes and maintenance. K-means steps. Initialize centroids. K-means clustering begins by choosing initial centroids, which act as starting centers for the clusters rather than actual data points. Each data point is assigned to the nearest centroid, and the algorithm repeatedly adjusts the centroids based on those assignments. Because these starting positions guide the process, they can strongly affect the final clustering result. When choosing centroids manually, place them in distinct, well-spread regions of the data, rather than grouping them together. Use the scatter plot to pick starting points near the expected clusters, such as low, moderate, and high strain and displacement areas. The initial positions do not need to be exact, but they should give the clustering algorithm a sensible starting point for separating the data. Choosing initial centroids in k-means requires both technical judgment and understanding of the data. Noise and outliers can make real clusters hard to identify, and selecting an outlier as a center can distort the results. Visual checks and domain knowledge help choose better starting points, which strongly influence whether the final clusters reflect meaningful patterns. Python code. Initialize centroids. This segment demonstrates how to manually choose starting centroids for k-means clustering using bridge sensor readings as engineering data. Before any data points are assigned to clusters, the initial centroids are plotted to show where the clustering process begins. We begin by importing the key tools for the k-means clustering demonstration. NumPy supports efficient numerical work with arrays, while Matplotlib's plotting tools help create visualizations. Together, they provide the foundation for manipulating data and displaying clustering results. We create a small, deterministic dataset of sensor readings using two NumPy arrays. One stores strain measurements in microstrain, and the other stores matching displacement measurements in millimeters. Together, these values will later form coordinate pairs for analysis. The strain and displacement arrays are combined into coordinate pairs using NumPy's column stack function. This creates a two-dimensional dataset where each row is one point with two features, strain and displacement. The expected shape is then set to 9 rows and 2 columns so the data structure can be checked for correctness. The code first verifies that the point's data has the expected structure, 9 data points with 2 features each. If the shape is different, it raises an error to signal that the sensor data is not in the required format. This early check helps catch data structure problems before any further analysis is performed. The k-means process begins by manually choosing 3 initial centroids, each defined by strain and displacement values. These centroids are placed in distinct areas of the dataspace to give the clustering a strong starting point. They are also labeled C1, C2, and C3, so they can be easily identified in later analysis or visualizations. The code verifies that the centroids have the expected shape, 3 points, each with 2 features. This check helps ensure the k-means algorithm receives valid input. If the dimensions are wrong, it raises an error so the problem is caught before clustering continues. This example shows how to manually choose starting centroids for k-means clustering. It first gives a quick summary of the dataset by reporting the number of data points and features. It then explains that these centroids are only initial guesses, not final cluster centers, and should be distinct and spread out to give the clustering process a strong starting point. A scatter plot is created with a clear 7x5 figure size to show the sensor data. Strain values are placed on the horizontal axis, and displacement values on the vertical axis. The readings are shown as steel blue points and labeled for the plot legend. Centroids are added to the plot using a scatter plot. With their coordinates taken from the centroid array, they are shown as large crimson X markers so they stand out from the other points, and they are labeled as initial centroids to make their purpose clear. To label centroids on a plot, pair each label with its coordinates and place the text near the matching point. The Matplotlib text method is used to position each label with a small offset, so it does not overlap the centroid marker and remains easy to read. The plot is labeled to make the data clear. The x-axis shows strain in microstrain, and the y-axis shows displacement in millimeters. Its title, Manual Initial Centroids for K-means, indicates that the visualization focuses on manually chosen starting centroids for a k-means clustering example. To finish the visualization, turn on the plot grid to make data points easier to compare. Add a legend to distinguish the sensor readings from the initial centroids, and then display the plot. These final steps make the chart clearer and ready to view. This script shows how to manually choose starting centroids for a k-means clustering example using bridge sensor measurements. It creates coordinate pairs from strain and displacement data, selects 3 distinct centroids spread across the data space, and checks that the data and centroids have valid shapes. The result is a scatter plot with sensor readings and labeled initial centroids, illustrating the starting point for k-means and how centroid placement can affect later clustering. Centroid update. After each data point is assigned to its nearest centroid, the centroid is updated to represent the average position of all points in that cluster. It is not an original data point, but a calculated center based on the cluster's measured features. This update helps refine the initial rough centroid positions by repeatedly moving them toward the true center of their assigned points. Updating centroids means recalculating each cluster center so it better matches the average of the data points assigned to it. In a delivery route example, centers may shift to represent short, efficient routes or longer, fuel-heavy routes more accurately. Repeating this process of assigning points and updating centers gradually refines the clusters because the nearest center can change after each update. When updating k-means centroids by hand, group the assigned points in each cluster, find their center, and move the centroid there. Large shifts suggest the starting centroid was a poor fit, while small shifts indicate the cluster is becoming stable. Repeat until the centroids or point assignments stop changing, and use plots and domain knowledge to check that the results make sense. Python code. Centroid update. Manually updating centroids helps make k-means clustering easier to understand. Using a small root dataset keeps the calculations visible, but any engineering interpretation should be checked carefully. We import NumPy to handle numerical calculations and work efficiently with arrays, such as data points and centroids. We also import Matplotlib's plotting tools to visualize the data points and centroids, making it easier to see how clustering changes over time. We create a NumPy array of 6 data points, where each point pairs a route's distance in miles with its fuel use in gallons. This gives a simple 2-dimensional dataset for studying the relationship between distance and fuel consumption. It also provides the data needed to visualize and understand clustering behavior in k-means. We start k-means clustering by choosing 2 initial centroids as points in 2-dimensional space. The first is at 2 and 0.7, and the second is at 9 and 2.9. These rough starting points guide the algorithm, and their choice can affect how the clustering converges and what final groups are found. We first confirm that the data has the expected shape, 6 points with 2 features each, and 2 initial centroids with 2 dimensions each. These checks catch shape errors early, so the rest of the code can run on correctly formatted data. To assign points to centroids, compare each point with every centroid and calculate their Euclidean distances. This produces a distance matrix, where each row represents 1 point and each column represents 1 centroid. Each point is then assigned to the centroid with the smallest distance. To update the centroids, first make a copy so the original positions are not overwritten too early. Then, for each cluster, find the points assigned to it, and if any exist, replace that centroid with the average position of those points across all dimensions. This step summarizes a manual update of k-means centroids. It shows the current cluster assignments, then compares the old and new centroids in a rounded, easy-to-read form. The key point is that each new centroid is the average of the points assigned to its cluster, so it may not be an actual data point. The plot uses different colors to show the two clusters, making their assignments easy to distinguish. The data points are displayed clearly, while the initial centroids are marked as black crosses and the updated centroids as larger red stars. This highlights how the centroid positions change after the update. To show how centroids move during an update step, each old centroid is paired with its new position, and an arrow is drawn from the old coordinates to the new ones. The arrow includes its head, uses a small head width, and is colored gray, so the movement stands out clearly on the plot. The plot is prepared by labeling distance in miles on the x-axis and fuel use in gallons on the y-axis. A title identifies it as a centroid update after one assignment step, and a lightly transparent grid improves readability. The finished plot is then displayed to help interpret the centroid movements and assignments. This script shows one manual iteration of k-means clustering using route distance and fuel usage data. It assigns each point to the nearest of two starting centroids using Euclidean distance, then updates each centroid by averaging the points in its cluster. The output compares the initial and updated centroids and shows the resulting cluster assignments. A visualization highlights how the centroids move after the assignment and update steps. Centroid update. After assigning each data point to its nearest centroid, k-means updates each centroid to better represent its cluster. The centroid is not a real data point, but the average position of all points in that cluster across each feature. By moving centroids to these averages, the algorithm gradually improves the cluster centers from their initial positions. The centroid update step recalibrates each cluster center after points are first grouped. If a center does not represent its assigned points well, it moves toward where those points are concentrated, such as closer to downtown when most delivery addresses are there. The updated centers are then used in the next reassignment cycle, helping the clusters gradually stabilize. When updating k-means centroids, the key is knowing which points belong to each cluster, because those assignments determine the new centroid positions. Small assignment changes, especially in small clusters or with outliers, can noticeably shift the result. The process repeats until centroids or assignments stop changing, but a stable solution is only useful if the chosen features and clusters make sense for the system being studied. Python code, centroid update. This example shows how to manually update centroids using a small set of pump sensor observations. It focuses on summarizing assigned engineering data and recalculating centers without using machine learning libraries. We import NumPy to work efficiently with numerical data in arrays and matrices. We also import Matplotlib's plotting tools to visualize data points and centroids, which helps show the clustering process. We store each pump observation in a two-dimensional NumPy array with pressure in PSI and flow rate in gallons per minute. This structure keeps the measurements organized and makes them easy to analyze using NumPy array operations. The snippet defines two pump sensor data points using pressure and flow rate as features. One point records pressure 86 with flow rate 162, and the other records pressure 79 with flow rate 155. These points are used to update centroids in a manual k-means clustering process. We begin clustering by manually choosing two starting centroids. These points, located at 45 and 100, and 90 and 165, serve as the initial references for grouping nearby data points. We first confirm that the data has the expected shape. The point data contains 6 observations with 2 features each, representing pressure and flow. And the centroid data contains 2 initial centroids with the same 2 features. These checks ensure the data is properly formatted before further processing. To find how close each point is to each centroid, we first compute their differences across all features. We then calculate the Euclidean distance by squaring those differences, adding them across the feature dimensions, and taking the square root. The result is a distance matrix showing how far every point is from every centroid. Each data point is assigned to the nearest centroid by choosing the smallest distance. These assignments form 2 clusters, one for each centroid. The centroids can then be updated by taking the average of the points in their assigned clusters. To update centroids, compute the average position of the points assigned to each cluster. Each centroid is then moved to the center of its cluster, so it represents the mean location of the data points assigned to it. We measure how much each centroid moved by calculating the Euclidean distance between its original and updated position. Then we report the starting centroids, the updated centroids rounded for clarity, and the number of points assigned to each cluster. Finally, the rounded movement values show how far the centroids shifted, helping indicate whether the clustering process is converging. The visualization compares clustered data points with their centroids before and after an update. The data points are shown in colors based on their cluster labels, while the initial centroids use a distinct marker, and the updated centroids use a larger star marker. This makes it easy to see how the centroids moved relative to the data. The plot is prepared by labeling pressure in pounds per square inch on the x-axis and flow rate in gallons per minute on the y-axis. It is titled Manual K-Means Centroid Update, with a light grid added for readability. The final display shows the data points along with the initial and updated centroids. This script demonstrates one manual iteration of K-means clustering on pump sensor data using pressure and flow rate. It starts with 2 centroids, assigns each reading to the nearest one, then updates the centroids by averaging the points in each cluster. It reports the new centroid positions, cluster sizes, and how far the centroids moved, then plots the data with the initial and updated centroids. The goal is to show the core K-means process without using machine learning libraries. Cluster interpretation. Cluster context. In K-means clustering, groups are formed from numerical similarities, but the algorithm does not know what those groups mean in an engineering context. A cluster is only a pattern in the chosen variables, not automatically a fault type or physical condition. For example, machine data grouped by vibration, temperature, and speed may suggest normal or abnormal operation, but that interpretation depends on context such as operating conditions and sensor calibration. Without that context, clusters can be mistaken for real phenomena when they may reflect data collection or scaling choices. Visualizations help engineers judge whether clustering results are meaningful. Scatter plots and 3-dimensional views can show whether clusters are compact, overlapping, or driven by one variable. In energy or traffic systems, plots may reveal that clusters reflect factors like building size, time patterns, weather, or sensor location rather than the intended categories. This context helps prevent misinterpretation and checks that clusters match known engineering behavior. Engineering knowledge is essential for interpreting clusters meaningfully, not just mathematically. Patterns found by K-means should be checked against the physical system, measurement process, and operating conditions. For example, unusual sensor or water quality readings may reflect real problems, but they may also come from changing loads, seasonal effects, maintenance history, or instrument errors. Clustering is useful for finding patterns, but domain knowledge is what turns those patterns into reliable insights. Python code, cluster context. Interpreting clusters requires engineering judgment. K-means can reveal patterns in data, but it does not explain their causes. Visual plots are useful for checking clusters and avoiding unsupported labels. We begin by importing NumPy to handle numerical data efficiently with arrays, matrices, and mathematical operations. We also import Matplotlib's plotting tools so we can visualize the data and clustering results. The data is generated with a fixed random seed so the results are reproducible. 2 synthetic building groups are created: small buildings with lower electricity use and peak demand, and large buildings with much higher values and greater variation. Each group contains 18 data points with 2 features, producing 2 clearly distinct clusters for analysis. The small and large observation sets are combined into one dataset using NumPy's vertical stack function. The result should contain 36 data points with 2 values each, and an assertion verifies this shape so the data is ready for later analysis. We start k-means by manually choosing 2 initial centroids, one near 70-20 and another near 280-50. These starting points are chosen to separate smaller and larger building data. We also check that there are exactly 2 centroids, each with 2 dimensions, matching the structure of the data. The k-means update runs for 4 iterations. In each pass, it measures the Euclidean distance from every data point to the current centroids, assigns each point to its nearest centroid, and then recalculates each centroid as the average of the points in its cluster. This gradually moves the centroids toward the centers of their assigned groups. The code counts how many buildings fall into each k-means cluster, then reports the size of each group. It explains that the buildings were grouped by numerical similarity, mainly driven by building size and peak demand. It also warns that these clusters should not be treated as specific usage types without additional context about the data. This plot visualizes clustering results for monthly electricity use and peak demand. Each data point is shown by its electricity use on the x-axis and peak demand on the y-axis, with colors indicating cluster membership. The cluster centroids are highlighted as large red X marks, and labels, a title, and a subtle grid make the chart easier to interpret. The goal is to identify patterns in the data before drawing explanations. This script applies k-means clustering to synthetic building data using electricity use and peak demand. It groups 36 observations into 2 clusters, mainly separating smaller buildings from larger ones by numerical similarity. After several centroid updates, it reports the cluster sizes and shows the separation visually. The key caution is that these clusters reflect patterns in the numbers, not confirmed building usage types, so they should not be overinterpreted without more context. Cluster trends. Cluster trends are patterns that appear after grouping data, and they can give engineers early insight into operating conditions. In k-means results, clusters may suggest states such as stable settings, high wear, or unusual combinations of measurements. These patterns help simplify large datasets, but they should not be treated as proven categories. Because k-means always assigns points to clusters, cluster trends are best viewed as hypotheses that need further validation. When interpreting cluster trends, remember that a simple 2-dimensional plot may hide patterns from other variables used in the clustering. Clusters that look similar may differ in unshown dimensions, while apparent differences may not reflect the full model. Engineers should compare multiple views and judge results against known system behavior. since context can change what a trend means. When interpreting clusters, remember that patterns may reflect how the data was collected rather than the system itself. Sensor placement, sampling rate, seasonal effects, or operating conditions can shape the results, so visual patterns should be checked against domain knowledge and further investigation. Clusters are most useful when they raise questions about consistency, physical meaning, and possible actions for engineering analysis. Python code, cluster trends. Cluster trends should be interpreted carefully from an engineering perspective. In this simplified example, the sensor data is synthetic, and the plots are useful for forming hypotheses rather than making final conclusions. The script begins by importing NumPy for efficient numerical work and data handling, along with Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the script to compute with data and display trends clearly. To make random results repeatable, create a random number generator with NumPy and set its seed to 42. This ensures the same sequence of random values each time the code runs, which helps with debugging and checking results in data analysis and simulations. 3 operating condition centers are defined to generate synthetic sensor data for clustering analysis. Each center combines temperature, vibration, and pressure values, representing different machine states such as low, moderate, and higher pressure conditions. These centers provide the reference points used to simulate distinct groups of sensor readings. An empty collection is created to hold synthetic sensor data clusters. For each cluster center, random 3-dimensional noise is generated for 18 samples, with different variability in each dimension. This noise is added to the center to create points scattered around it, and the resulting cluster is stored for later use. The code uses NumPy's vertical stack function to combine separate clusters of generated sensor points into one unified array. This creates a single dataset that is ready for later analysis, such as clustering or visualization. We check the data array's shape to confirm it has 54 rows and 3 columns, meaning 54 observations with 3 features each. This safeguard verifies that the data was created and combined correctly before any further analysis. K-means clustering starts by choosing initial centroids from the dataset. In this case, 3 observations at positions 0, 20, and 40 are selected and copied, so the original data remains unchanged. These starting points guide the algorithm as the centroids move iteratively to reduce distances to nearby data points and form clusters. K-means clustering is updated over 6 iterations by repeatedly assigning points to the nearest centroid, and then moving each centroid to the average position of its assigned points. Each round uses Euclidean distance to decide the closest cluster for every data point. This iterative process gradually refines the clusters by reducing the distance between points and their centroids. The output summarizes how K-means grouped 54 unlabeled operating records into 3 clusters. It notes that the clusters reveal possible trends, not physical causes. For each cluster, the program reports how many records it contains and the average temperature and vibration, giving a concise view of the main patterns in the data. The plot visualizes clustering results for temperature and vibration data. Each data point is shown in a scatter plot and colored by its assigned cluster, while the cluster centroids are highlighted with large red X markers. The axes label the engineering measurements, and the title, grid, and display settings help make the cluster trends easier to interpret in context. This script demonstrates k-means clustering on synthetic sensor data. It creates 3 noisy groups representing different operating conditions, then repeatedly updates selected centroids to form clusters. The results summarize each cluster by point count and average temperature and vibration, and a plot shows the color-coded groups with centroids marked. The example highlights that clustering can reveal patterns, but those patterns still need careful engineering interpretation. Practical engineering judgment. Clustering results should be treated as hypotheses, not final answers. Algorithms such as k-means can reveal patterns in sensor data, but they cannot decide whether those patterns are meaningful or physically plausible. Engineers must use domain knowledge to connect clusters to real machine states, faults, environmental changes, load differences, or sensor placement effects. In short, the algorithm finds structure, but engineering judgment gives it real-world meaning. When interpreting clusters, remember that results depend on how the data was collected, scaled, and displayed. Variables may differ in meaning, reliability, and range, so giving them equal weight can distort the patterns. Engineers should check whether clusters make sense using real-world knowledge and records before drawing conclusions. Use clusters as a guide for investigation, not as proof of cause and effect. They can reveal patterns, anomalies, and useful ways to simplify data, but their meaning should be checked against stability, physical principles, and practical decision risks. Interpretations should change when new data or expert judgment suggests a better explanation. Python code. Practical engineering judgment. Interpreting clusters requires engineering judgment because visual plots can be misleading. In k-means, results also depend on how the data is scaled, so scaling choices can change the clusters you find. The script begins by importing NumPy for working with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the environment for data manipulation and plotting in Python. A random seed is set, so the code gives the same results each time it runs, supporting reproducibility. The dataset is then created with 2 numeric arrays, one for building floor areas and one for monthly energy use. Together, these values represent the relationship between building size and energy consumption. An occupancy array is added to represent how many people are in each building, giving more context for understanding energy use. The floor area and monthly energy data are then combined into one 2-dimensional matrix, where each row represents a building and each column represents a feature. This prepared dataset is ready for later analysis and clustering. We first confirm that the dataset has the expected shape, with 9 observations and 2 features. Then we check that the occupancy values match the number of data rows, so every building observation has a corresponding label for reliable analysis. This k-means clustering function starts with data points, initial centroids, and a chosen number of iterations. In each iteration, it measures the Euclidean distance from every point to each centroid, assigns each point to its nearest centroid, and then updates each centroid to the mean of the points assigned to it when that group is not empty. The function returns the final cluster labels for the data points and the updated centroids. K-means begins by choosing initial centroids from selected rows of the dataset to provide varied starting points. The algorithm is then run on the unscaled data, repeatedly assigning points to the nearest centroid and updating centroid positions. The final output gives each data point a cluster label and the final centroid locations. Before applying k-means, the data is standardized so each feature is on the same scale. We find the average and standard deviation for each column, then subtract the average and divide by the standard deviation. This gives each feature a mean of 0 and a standard deviation of 1, helping k-means treat area and energy equally. We choose 3 rows from the scaled data as the starting centroids for k-means, since these initial points can affect the final clusters. The custom k-means function then assigns each data point to its nearest centroid and repeatedly updates the centroids using the assigned points. The output gives the cluster label for each point and the final centroid locations, helping show how scaling influences the clustering result. The code compares k-means cluster labels from raw data and scaled data to show that scaling can change how points are grouped. This means the same dataset may lead to different cluster interpretations depending on pre-processing. Before acting on the results, use context such as occupancy, logs, physical principles, and engineering judgment. A clear scatter plot is created to show each building's floor area against its energy use. Each point is colored by its scaled k-means cluster using the Viridis color map, with point sizes chosen for easy visibility. This helps make the clustering patterns easier to interpret visually. This code adds occupancy labels to a plot, so viewers can judge building energy patterns more effectively. It loops through each building and places a small text label near its plotted area and energy use values. Each label shows the number of occupants followed by P, helping connect the clusters to how many people use each building. The plot labels show building floor area on the horizontal axis and monthly energy use on the vertical axis. Its title highlights the main point. K-means can form clusters, but interpreting what those clusters mean requires engineering judgment. The plot is finalized by adding a color bar to show which colors represent the clusters found by the scaled k-means algorithm. A light grid improves readability, and the layout is adjusted so the figure elements do not overlap. The completed plot is then displayed to help interpret the clustering results in their engineering context. This example shows that scaling can strongly affect k-means clustering. A small building energy dataset is clustered using floor area and energy use, first in raw units and then after scaling, and the cluster labels change. The key lesson is that clustering results depend on how variables are measured, so they should be interpreted with engineering context, such as occupancy. In this lecture, you learn to explain how unsupervised learning differs from supervised prediction in engineering analysis. Implement k-means clustering with manual centroid assignment and update steps. And interpret clusters cautiously using plots and engineering knowledge. In the next lecture, Lecture B, we will go over time series features.
Thank you for your attention. See you all in the next lecture.